So today's speaker is Keisuke Harigaya. Keisuke did his PhD at Tokyo University, IPMU, and then went on for postdoc to UC Berkeley, Princeton, CERN, and so last year he started a faculty position at the University of Chicago. Keisuke is working on Axion, as you can see, as one of the topics he's working on, and he will be telling us about the cosmology of axion rotation. So please.
Thank you for invitation and introductions. I'm Keisuke Harigaya from the University of Chicago. So today I'd like to talk about my recent work on cosmology of axion rotation based on these papers. So, I study particle physics and cosmology and interested in questions such as what is dark matter, how did the cosmic inflation occur, how was the baryon universe created, so why does QCD preserve CP symmetry, or what set the Higgs potential parameters, especially the mass term. And today, I will talk about the three of them: dark matter, baryon symmetry, and a strong CP program. So here is a summary of my presentation. Today, I would like to introduce new cosmological dynamics of the axion that explain dark matter for axion coupling constant much larger than the prediction of conventional mechanism, create the baryon asymmetry universe, and has implication for new physics beyond the QCD axion and actionlike particle. So here's a more concrete outline. So I first introduce axion study from the strong CP program and introduce axion dark matter. So then I will introduce a new dynamics, the rotational axion in the universe, and discuss its implication to axion dark matter. So then I will argue that the same dynamics, the rotation, can also create the baryon asymmetry of the universe. And we obtain some predictions on the axion parameters or BSM parameters. And then summarize the talk. And let's start from the introduction. So axion was originally introduced to solve the strong CP problem. So we know that the neutron is composed of positively charged up quark and negatively charged down quark. So then we may naively expect that the neutron should have non-zero electric dipole moment as large as the size of the neutron, namely femtometer. But the observation shows that the neutron element should be much, much smaller than this naive expectation. So this suggests that the strong interaction that bind quarks into neutron preserve a fundamental symmetry called CP symmetry, charge conjugation and parity symmetry, that can forbid the neutron EDM. But on the other hand, we also know that the CP variation from the quark masses or the Yukawa interaction is essential in order to obtain the CP variation in the weak interaction, namely the secant phase. This discrepancy between the CP preservation in the strong interaction and a variation in the weak interaction is called the strong CP problem. It is one of the most serious mysteries of the standard model. The QC action can solve this strong CP problem. So we start from the U1 global symmetry that has QCD anomaly, called the Pechak-Quinn symmetry or PQ symmetry. And we assume that this U1 symmetry is spontaneously broken so that we obtain a Nahm-Goldstone boson called the QC axion. So then because of this QC anomaly, in the Lorentz effective field theory, the axion should couple to the gluon field strength suppressed by a scale called the decay constant. So this decay constant is essentially the symmetry breaking scale of the Pechak-Quinn symmetry. So in terms of potential shape, decay constant corresponds to the radius of the Wien-Botero potential with which the pitch symmetry is spontaneously broken. And action field is the angular direction of this complex field. So what happened is that although this action potential is nearly flat, because of the interaction with the strong gluon and the strong QC strong dynamics, action obtains a non-zero potential and is driven to the minimum where the strong interaction preserves the CP symmetry. So that the neutron EDM as well as other CP variation in the QCD such as the decay of the meson into a pair of baryons vanishes. And this is how the strong CP problem can be solved by the QCD axiom. So another interesting point about the QCD axiom is it is a natural dark matter candidate. So for sufficiently large decay constant, because of its weak coupling with the QCD, axion mass becomes smaller and smaller. And also, its coupling with other particles also becomes smaller and smaller. So axion is naturally light and weakly coupled, and hence is naturally long-lived to be a good dark matter candidate. A similar motivation for as a dark matter works for action-like particle, which is a pseudo-number ghost boson from some global symmetry breaking, but does not solve the strong CP problem. So again, in the limit where this global symmetry is good, it is naturally light, and in the limit where the decay constant is sufficiently light, it's weakly coupled. And the action-like particle can be also naturally long-lived to be a good dark matter candidate. So in today's talk, I mainly consider QC action, but also discuss action-like particle in passing. Anyway, because of this motivation, so there are many action search conducted and planned. So in this plan, x-axis axion mass and y-axis is an axion photon coupling that is inversely proportional to decay constant. This orange line shows the prediction of the QCD action. And other shaded regions are excluded. And the lightly shaded regions show the prospects of various experiments. So you can see that these many experiments could eventually cover the viable parameter space of the QC actions. And this figure was taken from this website, which you must know. The question we should ask on this plan is on which point in this parameter space can the QC action or action-like particle can be dark matter. So namely, it is not enough to argue that they can be naturally stable. We must consider how they were populated in the early universe to explain the observed dark matter abundance. And of course, there are standard understanding of that. So the conventional mechanism is called the misalignment mechanism. So what's that? Because of the lightness of QC action, there really is no reason that action should sit at the minimum of the potential in the early universe. Rather, we expect that action field displaced from the minima by some angle called the misalignment angle. Then as the universe cools and the hyperexpansion rate or hyperfriction becomes smaller, the action begins oscillation around the minimum, like this. And the action oscillation behave as matter. And this is just the 1D slice toward this angular along the action direction. So then we can compute the abundance of the action as a function of the decay constant, the axion mass, and the misalignment angle, which we call theta I. So for the case of QC axion mass is determined by the decay constant. So there are only two parameters. And here is a formula for the axion energy density normalized by the dark matter abundance. And this is a formula. So the implication is the following. So if the misalignment angle is a natural one or naive one, order one, the top black circle is the prediction of the misalignment mechanism. But if we are happy with taking smaller misalignment angle, like 0.1 or 0.01, smaller axion mass, or smaller axion thermal particle coupling, it's also consistent with the idea of QC action dark matter from this conventional misalignment mechanism. On the other hand, in the parameter region where axion mass is large, or the axion coupling is large, the misalignment mechanism underproduces QC action as dark matter. And we can repeat the same analysis for action-like particle, which reside outside this QCD band. So if the misalignment angle is order 1, this gray band is a prediction of misalignment mechanism. So, and if the misalignment angle is smaller, the region below this gray band is also consistent. But basically above the gray band, the misalignment mechanism underproduces action-like particle as dark matter. So that's the conventional understanding. But today, I will present some new cosmological dynamics of the action field that enhance action dark matter abundance and predict larger couplings, create baryon symmetry universe, and have implication for action searches and new physics beyond the action. So that's what I would like to talk today. Okay, so let me introduce the new dynamics. So in the conventional misalignment mechanism, it is implicitly assumed that the initial action field velocity is negligible. So that the action abundance, dark matter abundance, solely comes from the potential energy of the action field. But on the other hand, what happens if the action field has non-zero initial angular velocity? So in this case, so the action dark matter energy density could come from potential energy plus the kinetic energy. So if the kinetic energy somehow goes to actions, action abundance will be enhanced. So I call such mechanism as a kinetic misalignment mechanism. So later, I will introduce how we can prepare certain special initial condition. But let me first explain some phenomenology, assuming such an initial condition. Okay, so yeah, the dynamics I will consider today. So it turns out that indeed, this action kinetic energy can be transferred into the action dark matter abundance via the process called the action fragmentation. So what's that? We have this action zero mode rotation, which is given by angular velocity times time. So let us look at the fluctuation of the action field around a zero mode motion. Now using this action potential, the cosine potential. So the equation motion of this fluctuation at the linear level is given by this. So here I decompose fluctuation into Fourier mode K. And so this is the linear level equation. And you can see that this is the equation motion of the oscillator with time-dependent oscillating frequency. Then we know what happened to that kind of system. So-called parametric resonance occurs. So x-axis is the amplitude of the oscillator, and this y-axis shows the potential of that oscillator with certain frequency. And for appropriately chosen Fourier mode K, here's what happened. Potential oscillate, and this field oscillate, and this fluctuation is exponentially amplified. So this phenomenon is called a parametrical resonance and has been discussed in the context of cosmology with preheatings. So the physics is essentially the same. So then what happened is that with this equation motion, so one can show that there indeed exists a resonance around around the natural frequency of the system, namely angular velocity or frequency of the axion rotation. And we can also compute the rate of the exponential amplification, which is given by the function of the axion mass and the frequency of the rotation. So then what this parametric resonance does is that it amplifies the fluctuation in a certain mode, which corresponds to the axion dark matter projection in a certain mode. So this transfer kinetic energy of the zero mode into axion dark matter balance. Then we can compute the number density of axion produced by this parametric resonance process in the following way. The number density should be given by the kinetic energy of the rotation divided by the energy of each quanta, axion quanta produced by this parametric resonance. Then kinetic energy is of course given by the angular velocity square times the radius square, so which is the decay constant square. And as we discussed, the typical energy of the quanta is as large as the frequency of the rotation, or angular velocity. So then taking the ratio, you find that the number of density action produced by this parametric resonance is as large as the angular velocity times decay constant square. So this is nothing but the angular momentum of the axion rotation in the field space. So in terms of this field theory, this is nothing but the conserved charge associated with the UN Pichagin symmetry, the Pichagin charge. So the upshot is parametric resonance produce axion number density as large as a Pichagin charge density. So the phenomenological implication is that in the parameter region of the axion, where the conventional misalignment mechanism underproduce QC reaction as dark matter, this extra contribution from the kinetic misalignment mechanism can indeed populate the axion as dark matter. So this will be good news for the experiments such as Axion, Ramforce, and so on, that are sensitive to the large axion mass and the large axion photon turbulence. So what they detect could be axion dark matter indeed. Okay, then let's now come back to the question: can we prepare such a special initial condition, the angular velocity of the axion field? So how large angular velocity or how large Pichagin charge density do we need? So we know, as we discussed, number density of axion is as large as the number density of the Pichagin charge density. So then, using the relation between axion, using this the fact that the axion energy density should be given by a mass times a number density, so we can compute the axion energy density normalized by the observed dark matter density as a function of the axion mass and the Pichagin charge density normalized by the entropy density of the universe. So here it is convenient to normalize the Pichagin charge density by the entropy density because both the Pichagin charge density and the entropy density decrease in proportion to the cubic of the scale factor of the universe via the expansion of the universe. So once we create a Pichagin charge, and if normalized by entropy density, it is conserved. So this is a very convenient formula. So for example, for the decay constant or QC action around 10 to 9 GeV, where axion mass is around 6 milli-electron volt, we need a Pichagin charge density normalized by the entropy density much larger than unity. So this is certainly much larger than what we could obtain via the Pichagin charge density from thermal path. So can we really obtain such a really large charge asymmetry? That's the key question for this kinetic misalignment mechanism. But it turns out that there indeed exists a mechanism known in the literature that was considered in the context of so-called affect time mechanism. So let me explain that. So in addition to the dynamics of the angular direction of the pitch-acquainted symmetry breaking field, namely axion, let us consider the dynamics of the radial direction, this blue direction, or this what I call S here. So again, we can employ the mechanism used for the affect time mechanism by considering this radial direction dynamics. So what do we do? Let us assume that like a misaligned mechanism of the axion direction, angular direction, let us assume the large displacement of the radial direction from the minimum towards a large field value. So as large as the position of this red ball, while a minimum is this red circle. Then for such large initial field value, radial field value, higher order terms in the potential of the pitch-acquainted symmetry breaking field may be effective. And in particular, it is quite plausible that some of them explicitly break the Yuan pitch-acquainted symmetry so that this angular direction has non-zero potential energy. Then what happens is this potential gradient to the angular direction initiate angular motion by the kick to the angular direction, like this. After this rotation is initiated by this kick, the radial direction field value decreases because of the expansion of the universe. And then higher order term in the potential of the PQ breaking field that explicitly break the pitch-acquainted symmetry is no longer effective. But because of the inertial motion, the P continues to rotate, the complex field continues to rotate, approximately conserving the angular momentum. Field is nothing but natural charge or conserved charge associated with this Yuan pitch-acquainted symmetry. Like this. So then the answer to the question of how can we obtain a such it requires large pitch-acquainted charge density is this initial large field value, radial field value. The angular, the pitch-acquainted charge or angular momentum in the field space is proportional to the square of the rotation, the radius of rotation. So if this initial field value is sufficiently large, like GAD scale, may potentially cross the Planck scale, one can easily show that we can indeed obtain sufficiently large angular momentum or pitch-acquainted charge density required for the kinetic misalignment mechanism. So let me give some brief comment about the stability of this angular motion. So as I said, this rotation corresponds to non-zero pitch-acquainted charge. And this coherent zero-mode rotation corresponds to the Yuan charge, the pitch-acquainted symmetry stored in the zero mode. So in the language of the condensed matter, this is nothing but the Bose-Einstein condensation of the conserved charge. But here we consider the dynamics in the early universe, which has very, very, very large temperature. Then we might worry that, based on our knowledge on the condensed matter, if the temperature is high, this BC or the rotation might evaporate into excitation or particle antiparticle excitation at high temperature in the early universe. But it turns out the answer is no, but that can be shown by the thermodynamics in the following way. So we can just imagine that the system reached the thermal equilibrium between a zero-mode rotation and a particle antiparticle asymmetry in the bath. And they reach the thermal equilibrium. Then we can just, as we do in the standard thermodynamics, we can just compare the chemical potentials of the species. So this chemical potential is basically the energy per charge. So then the chemical potential of the rotation is just given by energy density divided by charge density, which is as large as the angular velocity of the rotation. So then again, this Pei-Chacun charge density is given by angular velocity times decay constant square. So then the antiparticle asymmetry in the bath reaches thermal equilibrium with the rotation. So then obtain a chemical potential as large as theta dot. Then using the standard knowledge on the relativistic thermodynamics, we see that the particle and antiparticle asymmetry in the bath is as large as the numerical factor 0.1 times angular velocity times temperature squared. And you can see that as long as the temperature is much smaller than the decay constant or the radius of the rotation, most of the charge is indeed stored as a form of rotation or BC rather than a particle-antiparticle asymmetry in the past. So this means that BC is stable against the possible evaporation into thermal excitation in the early universe. So by the way, this antiparticle charge density as large as 0.1 times angular velocity times temperature square will be used in the later part of this talk where we discuss the production of baryon asymmetry from rotation. So please remember this formula. So we can just apply. So far we have discussed the QC reaction, but we can just repeat the same analysis for the generic action-like particle. The phenomenological implication is in the parameter region where the usual kinetic misalignment mechanism underproduce action dark matter. This kinetic misalignment mechanism can populate enough amount of the action-like particles as dark matter, which prefer larger action thermal particle couplings. So again, which will be good news for some action detection experiments. Okay, so let's discuss how this baryon asymmetry can be produced from the axion rotation. So it turns out that this rotation can create a baryon asymmetric universe, and we call the mechanism axiogenesis, in analogy to so-called leptogenesis. Okay, let's start from the state where Pei-Chacun charge density is non-zero, so the axion rotates. Okay, so then we know that this Pei-Chacun symmetry is quantum mechanically broken by the QCD interactions, namely QCD anomaly. And so is the co-chiral symmetry. Then what happens is that via the QC strong dynamics, or called the sphaleron process, this Pei-Chacun charge density is destroyed while simultaneously creating a chiral charge of the quarks. So this is analogous to so-called leptogenesis, where we start from the lepton asymmetry of the universe, and we have lepton and a baryon symmetry, and the lepton and baryon symmetry had a weak anomaly, so that lepton asymmetry transferred into baryon asymmetry. This is very analogous to that. Pei-Chacun charge density is transferred into co-chiral charge via the QCD anomaly. So then, if there exists some baryon number violation that the thermal particle feels, so we can further transfer this co-chiral charge into baryon asymmetry. This baryon number violation could come from the standard process, namely weak anomaly, or weak sphaleron processes, or can come from some beyond the standard model interactions. So in this type of mechanism that we feature called axiogenesis, we can actually answer to some three questions of the universe. Just sorry, basically from the QC action plus alpha. Okay, let us first consider the minimal case where we utilize baryon number violation in the standard model, namely weak sphaleron process. So here is the whole picture. So as I argued, Page-Green charge density or the action rotation, right? Angular momentum of action rotation is transferred into co-chiral charge via the QC process. And because co-chiral symmetry has weak anomaly, and the baryon symmetry also has a weak anomaly, this co-chiral symmetry is further transferred into baryon symmetry via the weak sphaleron process. Since this is dictated by the standard process, this transfers are indeed effective before the electric phase transition, so that baryon asymmetry reach thermal equilibrium value. Then using a formula we discussed, we can estimate the baryon asymmetry at given temperature to be a numerical factor around 0.1 times angular velocity of the rotation, the chemical potential rotation, times temperature square. Then baryon number production stops upon the electroweak symmetry breaking or electric phase transition because the weak boson become massive and much heavier than the temperature, and this electroweak process become very ineffective. So baryon asymmetry of the universe is fixed at the electric phase transition, and given by the numerical factor times angular velocity at the electric phase transition times the electric phase transition temperature square. That's the formula. So now let's try to make prediction. The scenario has three free parameters. One is the angular velocity of the action and decay constant of the action. Then assuming a QC action, the action mass is predicted from decay constant. Now let us also take, for now, electric phase transition temperature, EW, as a free parameter. We know that in the standard model, this is around 100 GB, but let me for now take this free parameter for the reason you will immediately see. So then let's try to explain both dark matter and baryon asymmetry universe from the Axion rotation and the electric sphaleron process. So we have three free parameters and two density to fit, and 3 minus 3 of course 1. So then by using those observable, we end up with the one free parameter. If we take that to be the decay constant, QC action decay constant, now electric phase transition temperature is predicted as a function of the QC action decay constant. Yeah. What can we learn from this equation? Unfortunately, for the canonical so-called DFSZ and KSVZ axion model, astrophysical law 1 requires the decay constant should be above few times 10 to 8 GeV. Then using that constraint, one can see that electric phase transition temperature should be higher than a standard prediction, namely around 100 GeV. So unfortunately, this minimal case that doesn't work. But the good side is that we can make this scenario work by introducing some new physics that couples to the Higgs boson to raise the electric phase transition temperature. And then once we do that, we can basically predict the property of new physics or mass scale the new physics as a function of the QC action decay constants. So this will provide this can potentially provide a new connection between electric scale physics and the QC action physics. So it will be very interesting to construct a concrete model with higher electric phase transition temperature and make prediction on the parameter of such models. So this is the implication for this usual standard DFSZ or KSVZ action. What about the other model? So there exists a model where the coupling of action with nucleon, electron, and photons are suppressed in comparison with the usual KSVZ or DFSZ model, which is often called astrophobic action, because action doesn't have some coupling that is relevant for astrophysical constraint on the action. In such model, so we can obtain that we can make the decay constant below 10 to 7 GeV consistent with those astrophysical bounds. In particular, if decay constant is a few times 10 to 6 GeV, this the predicted electric phase transition temperature is consistent with the standard model prediction. So this scenario basically predicts the action parameter around here that can be proved by the experiments such as lamppost, this red circle on this corner. Yeah, so it will be interesting to probe this parameter region to see if this minimal axiogenesis scenario can work. Okay. So now we discussed the QC action, but the same mechanism also works for action-like particles. Action-like particle generically has coupling with standard particles of fermions, Higgs, and the weak edge boson. So via those interactions, the charge density in the angular momentum in the axion rotation can be again transferred into the baryon asymmetry via the thermal processes and the weak sphaleron process. So then again, now assuming the standard model phase transition around 100 GeV, we have three parameters. So angular velocity of the axion, like particle, decay constant. And since we consider action-like particle, not QC action-like particle, mass is generically a free parameter. So we have three. Then 3 minus 2 equal 1. We have one free parameter. Then if we choose that to be the action-like particle's mass, we can predict the decay constant of the action-like particles via this formula. And this prediction is called, this scenario is called electrogenesis, and the prediction is shown by this blue shaded band. So you can see this electrogenesis. And this scenario, so here it is assumed that this action-like particles has a natural has an electromagnetic anomaly to have a natural coupling with photon. You can see the prediction is much larger than the prediction of QC action. So it is very interesting if some future experiments detect the action-like particle on this band of electrogenesis. So we will see. Okay. So far, we discussed the production of baryon asymmetry via the standard model interaction, namely the sphaleron process. But a similar idea also works for baryon number variation from beyond the standard model. So it might be Majorana neutral mass, or if you like supersymmetry, it might be R parity variation in supersymmetry, or any BSM that you like and contains some baryon number violation. So again, what happens is paychecking charge is transferred into co-carrier charge via QCD anomaly, and co-carrier charge is transferred into baryon asymmetry via those baryon number violating process. So in those kinds of scenarios, so we can make connection between the beyond the standard model other than the axion and the beyond the standard parameters. So assuming the QCD axion, so we have 3 types of parameters. The one is, again, angular velocity. So another is, again, axion decay constant. And another set of parameters is a BSM parameters relevant for the baryon number violating process. So then we have 3 kind of parameters, and we should explain 2 density, dark matter and baryon asymmetry. Then after requiring the cogenesis of dark matter baryon, we can obtain one non-trivial relation among BSM parameters and the QC action decay constant to provide some connection between BSM physics and the QC action. So here is some few examples discussed in the literature, maybe by me or my collaborators. So this baryon number, broadly speaking, this B mass cell number variation could come from Majorana neutral mass, but given by dimension 5, so Weinberg operator. Then in this scenario, it turns out the mass of the radial direction of the page-Jacobi symmetry breaking field, which is as large as a scalar mass scale in supersymmetry. If we embed the theory in the supersymmetric theory, it's predicted. So, and we can also consider baryon number variation that may exist in supersymmetry model called R parity variation. And in this scenario, we can make prediction on the magnitude of R parity variation as well as scalar mass. If we, for example, put more restriction, such as considering dimensionless R parity variation, also the SU5 relation among them, we can, for example, make prediction on the proton decay rate as a function of the decay constant and the scalar mass scale. And we can also consider some baryon number variation by sphaleron processes in some new gauge interaction beyond the electroweak gauge interaction. In this scenario, like electric phase transition temperature is predicted as a function of decay constant in the minimal axiogenesis. So we can make prediction on the mass of new phase transition temperature, which is as large as the mass of new gauge boson, as a function of the QC reaction decay constant. Okay, so here is a summary of my presentation. So today I would like you to remember two words. So one is a kinetic misalignment mechanism. So where the rotational action field produce axion dark matter. And this scenario favor axion dark matter with a decay constant much smaller than the prediction of the canonical scenario. So which is maybe good news for some experiments. And today we'll also discuss axiogenesis, where the axion rotation produces baryon symmetry universe. Then we obtain one relation between the BSM parameters and the decay constant if we introduce BSM physics, or if we just restrict to the very minimal model with no BSM interaction, the standard equiphase transition temperature. The model favors over astrophysics QC reaction with a mass around the 1 electron volt, which can be proved by some experiments. So today I focus on this dark matter production and the baryon asymmetry production. But it turns out that this rotation of the action field can do a lot of interesting cosmological role. So for example, this action rotation has a huge kinetic energy. And that the kinetic energy might dominate the universe. So once the universe is dominated by kinetic energy, its expansion history is very different from the standard radiation plus matter domination. And this can modify the primordial spectrum of the primordial gravitational wave if they are produced by from other sources, such as the inflation or the local cosmic stream. Also, if we, for example, introduce some extra gauge boson, which is called dark photon, and couple it to this axion rotation, it turns out that inhomogeneous dark photon fields can be abundantly produced by tachyonic instability. And this fluctuation, huge fluctuation, can produce gravitational waves, and which can be observed in the present universe. Okay, so that's all I want to say today. Okay, thank you.
Thank you very much for the interesting talk. So we have time for questions. So you can raise your hand or just speak up. But maybe to get us started, can I ask you something? So you discussed that parametric resonance in the beginning, so to produce dark matter. Does that dark matter thermalize when you produce it, or do you produce it all in one mode? Or so your estimate was kind of, I think, for
so we can compute the scattering rate of the axion fluctuation produced right after produced by the parametric resonance. So we can show the following. Just when these actions are produced, its scattering rate is comparable to the upper expansion rate. But after that, it rapidly became much smaller than upper expansion rate, because the axion number density becomes smaller and smaller. And also the axion self-interaction rate is basically proportional to this gradient energy, which is also redshifted. So then Yeah, it is true that there can be some effect, order one effect of the scattering, but I expect it will not change the density by more than order one factor. But it will be very important.
So it would be partially thermalized, or?
So actually, it is not thermalized for the following reason. What happens is the following. You may think that if the rate is as large as Happer expansion rate, it is thermalized. But what happens is once the scattering occurs, because this action number density is much, much larger than thermal density, what happens is that it goes to direction where action number density decreases. So then what happens is, although it can change the number density order one factor, but they're reduced, but then now make the scattering rate inefficient. So that it doesn't, it cannot lead to thermalization, but it can at the most change the spectrum by order one factor.
Okay.
So that's what I expect. But having said so, I think it's very important to just check the dynamics carefully, maybe via some numerical computation.
Yeah. Right. Well, I'm just wondering how it affects then kind of how it would affect the physics of dark matter, kind of how it interacts, or structure formation and all.
Yeah, structure formation will be also interesting.
Yeah, I was also going to ask maybe a little bit on that point. Have you thought about the production of mini clusters in this scenario from the decay of topological defects, leaving large perturbations in the dark matter density?
So I didn't do that by myself, but do you know Geraldine Sarvan? So her and her collaborator actually checked, they discussed this action mini cluster production as a result of action fragmentation and a parametric resonance. So it seems, according to them, they predict the heavier action mini cluster than the usual case of this post-inflationary page-Jacobian symmetry breaking with a decay constant around 10 to 11 GeV. To my understanding, that is because this production occurs at the relatively later time, so that the horizon mass is larger than the usual case. So I think we, in principle, to differentiate mechanism by maybe looking at mini clusters.
Yeah, I might ask also. I think the answer to this is no, but I haven't thought very carefully about it. But because you have this large changes in the value of the Axion field at early times, does this modify anything to do with like the birefringence, CMB birefringence constraints on?
So what happened is that if we choose a velocity such that the birefringence is observable, it turns out that it is too rapid and basically overproduce baryon asymmetry. So it seems that it's difficult to explain, the suggested birefringence.
Yeah, okay.
There may be a way, but yeah, so far the result seems negative.
Can I ask you something? For that, in order to get that large asymmetry, the page-Jacobian asymmetry, you introduced that higher dimensional operator. So how much does it, the result depend on n? So kind of the power of that operator, does it depend on it very much?
So first of all, let's see. The answer is yes. Let's see. For example, let us imagine that we say 5. What happens is that so then the action mass, the ratio of the action mass at the minimum and at large field value is not so significant because this is not so high dimension operator. But then after requiring that this action mass around the minimum is not disturbed to destroy the strong CP problem. That's, say, dimension 5 operator will not be effective. So it's better to have some larger, higher dimension operator like 9 or 10. So it does affect. So.
Oh, okay. So you probably anyway want to have something which doesn't spoil the strong CP problem.
Possible. Yes. Yeah.
So, but then it's consistent with kind of having it at dimension 10 and Planck suppressed operators.
Yeah. So first, from the perspective of the a quality problem, if you consider Planck suppressed operator, this n should be above 9 or 10. So then for that field value, we can just take sufficiently large initial field value. So then this for larger and larger field value, the gradient to the angular direction becomes simply larger and larger. So we can easily initiate the rotation. So once quality problem is solved, the rest is not difficult.
Okay, good. Good. Well, that's, other questions? Maybe one more thing on the axiogenesis scenario. So basically, if you take the minimal model, right, you said that the temperature of the electric phase transition would have to be larger, right? So what would we introduce to lower it? So you had one solution was basically to modify it in such a way that the axion photon coupling is smaller, or the other one was. Can you explain a little bit more on that?
So maybe we can first start from this one. So in this one, we just fix the electric phase transition temperature to be the standard one. So then the decay constant is predicted to be below 10 to 7 GeV. And for the usual mechanism, usual scenario, like DF is in a case with this is battery excluded via astrophysical constraint, like neutron staggering or supernova cooling and so on. So then what we have to do is consider the model where axion coupling with nucleon, electron, and photons are suppressed to make this decay constant smaller than 10 to 7 GeV. But then we can just, this standard electric phase transition temperature is fine for this mechanism to work. So on the other hand here, we just stick to the more canonical or usual model where astrophysical lower bound actually is very strong and like few times 10 to 8 GeV. So then what we need is to raise the electric phase transition temperature. Then for this, for example, we can introduce some new scalar field that couples to the Higgs, and their dynamics can change the electric phase transition temperature. And so that's another possible scenario.
Okay, good. Thanks for explaining it more. Any other last question? Well, if not, then let's thank Keisuke